Okay, let's go over the class reading assignment number 3 on optically transparent nanotube coatings on flexible substrates. Because of the class cancellation last week, I wasn't able to go over your answers. Some of you got the answers okay. There were some challenges and others. Let's go straight in and see where the problems are. So here is your article, Fabrication and Characterization of Thin Films of Single-Wall Carbon Nanotube Bundles on Flexible Substrates, all kinds of stuff I think you read. And the question number 1 is, what specific type of nanotube was used in the study? How is it synthesized? From what we discussed in class? 2 questions here. So the first thing is, what specific type of nanotube? So what does the question mean? Not what does it say? What does it mean? Is that what worked, right? You can use 20,000 nanotubes, but what worked for that specific purpose? What is the purpose? To find a replacement for indium tin oxide, right? ITO. That's the question. What specific type of nanotube worked in the study, was used in the study? Mainly it was one type, right? That's the question. Then how was it synthesized? So with that, let's go back to the paper, and I'll stop share and go to the paper straight off. So it's easy to see in an actual paper, right? I don't know if you can see that. Let's take a look. So that's the paper, right? You keep going down. We observed here the best results were obtained using chemically purified mixture of metallic and semiconducting single-wall nanotube bundles obtained by pulsed vapor ablation. So the laser SWNT was used. Okay, that's the one that actually worked. That's the answer to that question. So from our class assignment of you know how it's made, kind of like you have two things, you have two carbon rods, and then you use a laser. I just wanted to make sure you remembered that. One was the arc discharge, one is the laser, and so anything you had put how it's made, it's fine. Or if you can just Google it, that's fine too. Okay, that was question number 1. So it's the laser nanotube that worked. That was the main question. Question number 2. All right. If you were forced to find a structural similarity between nanotubes and polyacetylene, what would be your response? So the idea we are asking you is carbon nanotubes, right? So if you know carbon nanotubes, it can get wrapped in 2 ways, correct? So you can get 2 kinds of wrapping, right? Let me just put it this way. Okay. This is a nanotube. This is a nanotube, right? All benzene rings all everywhere, right? So this goes all the way everywhere, the whole 2-dimensional. On this side also you have benzene groups, correct? So this basically goes 2-dimensional. This is the fills up, correct? So what is polyacetylene? This is carbon nanotube, right? What is polyacetylene? Polyacetylene has 2 forms, correct? That's the trans, and that is the cis, right? You're asked to find a structural similarity, right? What is the question again? If you were forced to find a structural similarity between nanotubes and polyacetylene, what would your response be, right? So let's take a look at what we just drew here. This is trans, this is cis, right? This is carbon nanotube. Remember, in carbon nanotubes, it's just benzene groups, correct? Yeah, that's how it goes. Can you see the similarity? This side, right? This whole, this did all this from here, X, right? If you just looked at this part, that looks like trans CHX, correct? And if you look at this part, this one, that looks like cis, right? Turned around. So this could be a cis. This is your trans, right? So that's called the zigzag, right? Zigzag wrapping. This is the armchair wrapping. If you don't know what I'm talking about, go back to the slides and see nanotubes can be wrapped this way or that way. Gives you semiconducting metallic properties. So they are structurally similar to conducting polymers, at least in their insulating form, right? That was the idea. That's question number 2, right? What's 3? There does not appear to be a dopant here. Explain the conductivity. It's an easy and a tough question, right? Graphite is a conducting. Graphite conducts, right? Charcoal. Charcoal conducts electricity. No doping, right? No dopant. Diamond, insulator, right? Why? What I wanted you to talk a little bit more about, because as you're more seniors and graduate students, is that diamond is sp3, graphite is sp2, right? What is sp3 and sp2? sp3, right? Ethane. All 4 bonds are there. You don't have 3 bonds and 1 dangling. It's all there, right? So diamond is like this. Diamond is nothing but carbon, 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 everywhere carbon, right? The whole thing is carbon. All the bonds are connected. No hydrogens. So what is ethylene? Ethylene is that, correct? So do you have all 4 bonds on carbon in ethylene? You do, right? This is a sigma bond, sigma bond, sigma bond, sigma bond, sigma. But this is a pi bond, right? This is the pi bond. But you still have 4 bonds. What if you have in benzene and all the stuff in graphite, you have layers of just benzene, right? That's what graphite is. Just layers of benzene. There's one layer, there's another layer here. Right? I mean, I'm terrible at drawing all these things. So that's benzene, right? That's graphite. So what is graphite? It's just 1 bond, 2 bonds, 3 bonds, right? So if you look at these bonds, right? How are they connected? This pi bonds, right? This pi bond over here, this pi bond over here, each of this is a pi bond, right? Goes all the way through. So this one also has pi bonds. Right? So these pi bonds overlap. Since each bond is 2 electrons, these electrons in this band can be thought of as a sea of electrons. A sea of electrons. So when you apply a voltage, the sea of electrons can move between the sheets of graphite, even though all the 4 bonds are satisfied. There's no dangling bonds, okay? That some of you mentioned. There's only 3 bonds. No, no, no. It's an sp2. It's all the bonds are satisfied. So that's the answer. It's intrinsically conducting because it has C. Like metals don't have to be doped. Copper, you don't have to dope copper. Copper is conducting, right? That was the answer to that question. All right. In a few lines, describe how line patterning is carried out. So some of you did a decent job, but I've already shared this in a slide. I don't think you looked at it. So let me go back to whatever that is, what is that called? The, Blackboard, very first week. Go to the home page. Your week 1, Introduction to Materials. I'm opening the PowerPoint presentation I shared with you all. And you go back. I think I went all the way up to conductivity and then how it was discovered, the Nobel, remember that, this one? And then I also went into a little bit of nanotubes and then I stopped there. But if you keep going a little bit further, the Stone Age, Bronze Age and all that, right? And then we have line patterning of conducting polymers on slide number 66. What is it, right? It's very interesting. So just take a look at it. You take a computer, for example, draw letter A on the computer, right? Using word processor. Invert the image. Invert this image. So the screen becomes black and the letter A is still white, right? Invert the image on the computer and then print it out on a piece of plastic. Because the image is black, the plastic is all full of toner lines, and then there's an A where there is no toner on the plastic, correct? Just print it out on a piece of plastic. Take that plastic and you spray water or conducting polymer plus water. There's some kind of a solution of carbon nanotube ink. Spray it right on the piece of plastic that has this black toner and that A letter which has no toner. So this goes everywhere, including on the toner lines, right? Then you remove the toner by dipping it into a solvent and just sonicating it for a few seconds. The toner comes off the plastic easily, but whatever hit the plastic underneath, which didn't have the toner, sticks. So whatever pattern you want, this time it's letter A. You can print any circuit instead of the letter A, and you have the entire circuit pattern of conductive polymer or carbon nanotube on the plastic, and it's perfectly done. Okay, so you could do all kinds of stuff. You could, for example, you can print out. See, this is a plastic that's bent, but this little thing in the middle, that strip, is a conducting polymer that's been patterned this way. This is called line patterning. And you can see there's a piece of plastic in which all these lines have been made for sensors. Those darker lines is all carbon nanotubes. Okay, so that's line patterning. I mean, you did a decent job. Okay, but I just wanted to let you know, line patterning is not. It's not inkjet printing. It's not printing. It's patterning. Okay. So, for example, in the actual article, here are some line patterned. You can see here, finger patterned, etc. We could draw using the patterning technique. Okay, that's what I wanted to show you. Now let's go back to the questions. Great. So that's that. What is ITO used for? Why can't one just use aluminum? Easy question. ITO is indium tin oxide. It's used as a conducting metallic kind of conductivity on a and a transparent coating on for electronics. That's what ITO is. Can't use aluminum because aluminum is opaque. All metals are opaque, plastics are transparent. And so here you have an indium oxide, tin oxide, which is not a plastic, which is not really a metal, but it's kind of transparent and kind of conductive. That's the answer. Okay. What specific advantages do carbon nanotubes offer over ITO? Some of you got it correctly and missed some of the important ones. Carbon nanotubes are very flexible, right? You can bend it to a crease. You can open the crease and it still doesn't break. ITO breaks, right? That's a big advantage. Other advantage you might have missed is, remember, indium oxide, tin oxide, they're all metals, right? So if you coat it on a plastic, sometimes the weight of the indium tin oxide coating is almost equal to the weight of the plastic or even more. It's metallic, right? So the weight is very heavy, the screens, etc. Whereas carbon nanotubes is only a micron thick, so it's extremely featherweight compared to ITO. It's a huge advantage, right? So that's an advantage of carbon nanotubes over ITO. What advantages do ITO offer? I mean, that's an opposite question, right? Obviously, ITO is more conductive, right? Intrinsically more conductive than carbon nanotube. We still don't have high conductivity nanotubes. And for the same kind of thickness, etc., there's an advantage of ITO. The biggest advantage of ITO, of course, is the manufacturing process is well established. So it's a huge advantage. From mining all the way up to the coating is a very mature technology. So it's very hard to be able to replace that. So that's the advantage ITO offers over nanotubes. Describe all the nanomaterials used in the article. Again, all I wanted to use was, you wanted to see if you have eagle eyes. So nanomaterials, which means I'm only looking for nanomaterials, right? So 3 types of nanomaterials were used. I've underlined it here: purified laser, HIPCO carbon nanotubes, and purified HIPCO nanotubes. 3 kinds of nanotubes were used, and the nanotubes are the only nanomaterials used. Triton X is not is just a soap. It's not a nanomaterial, right? Some of you put Triton X. PET is polyethylene terephthalate. That's just a plastic. Some of you put P.PSS. That's just a conducting polymer. That's not nano. ITO PET is not nano. Okay, so that's the 3 kinds of nanotubes that we used are the only nanomaterials that are used in this paper. Going back to the questions, let's see. And how were they processed, right? The processing question is already there in the article, how they were processed. I don't know if you saw the processing question. The answer to that is, let me go back. How were they processed means how were they made into a film? Okay. Aqueous dispersions of bundles made from charged surfactants. Okay, great. In a typical procedure, this is the processing, right? A film, a plastic film, is immersed in a beaker containing nanotube dispersion, removed, air dried, batch sonicated, tonal line, right? And that's how you get the processing, is how do you convert a black powder into these. That's line patterning, right? That's the whole description of line patterning there. Great. Perfect. We stop that there. And go back to the questions. Last question. List 3 disadvantages of nanotubes. So not advantages. Some of you read the question wrong. Advantages already we've asked, right? You don't have to repeat it. Disadvantages. One key disadvantage, as you mentioned, is very small amounts are made. So the synthesis procedure and process is extremely archaic and alchemy, right? Just alchemy. Turn on something high, you get some nanotubes. So you can't have a technology based on BS like that. So the synthesis is still in its very infancy. So materials availability is not reliable, number 1. Number 2 is extremely expensive. If you can only make 20, 100 grams a day, imagine with that much power and so much catalyst used, is extremely expensive. So that's number 2. Number 3, you don't know what nanomaterials can do to your lungs if somebody throws this screen out and the nano carbon nanotubes go into the air, into the fish, aquatic, etc. You don't know what kind of damage it can cause. So whereas ITO has no issues, right? It's not a nanomaterial. It's well known. It's been here for like 50 years, so it's well established toxicity profile. Nanomaterials, especially nanotubes, toxicity profile is still in question. So that's the answer. Anything I have been unclear about, let me know. I'm trying to do as much as I can to get as many answers to you as I can, given all the cancellations. Next Tuesday is also a Monday schedule, so I'll think of something. We have kind of a challenging time, but it's fun. We'll get it. I'll get it across to you. Okay, don't worry. I'll do my best. Any questions? Let me know. Okay, good night.